Hello, welcome back. Okay, so I learned some things. I went off to do take care of some things around the house and listened to my stream, and I realized some things that I need to change. One of the big ones is I realized I was kind of boring myself, and I'm like, well, I'm interested in this topic, so why am I boring when I'm talking about it? And I realized part of it is I'm not describing everything I see. A lot of the things I'm describing are visual, where you have to look at the screen while I'm streaming. And I realized I don't want that. I want a stream where you can listen to it and get value out of it, even if you aren't looking at the screen, even if you're doing something else. I want a video. I want a stream that will hold up to podcast mentality of, I'm just going to turn on this video and put it in my pocket and listen to it over headphones. So I kind of want to support that and allow someone who's not looking at my screen to be able to get a lot of value out of it. So that means I need to describe what I'm seeing and also describe what I'm doing. Like, even if you are watching it, like, there are a lot of moments where I'm pausing because I'm trying to think, which is okay. That's going to be a normal part of the process of programming. But what am I thinking about? I need to answer that question before I go silent. So so those are things I'm going to work on. Those are hard goals. Those are big goals, and ultimately, it's going to change the way I program when I'm on stream. Am I live? I don't feel like I'm live. I guess I am. I can see the needle moving in OBS. Okay. So ultimately, what that means is I'm going to be concentrating more on the stream and less on programming. So that means programming will go slower while I'm streaming. And I think that's okay, because what I really want is I want to kind of explore and discover when I'm programming, um, what is the maximum coolness that you can have from a programming screen. Like, I've seen programming videos out there, and a lot of them are just not that interesting, even if the topic's interesting. And for kind of some of the same reasons. Like, either one of the common things is that you'll see a lot of programming videos on YouTube that skip over too much detail, so it's not really useful in that sense. Like, it doesn't go into the nitty gritty detail, and so that's one of my goals for this. By streaming the entire process, or at least a large chunk of it, you can see what I'm doing in a lot of detail, and you can kind of figure it out for yourself on from there. But another issue I'm having is I'm not describing enough about what I'm doing. I need to give enough detail about what I'm doing. So that's something I'm going to work on. Yeah, I just thought I'd share that with you. Another thing I realized when I was giving my explanation of how this all works, I realized that I failed to mention what a frame was. I meant to look that up and I didn't. So I did mention that a body consists of faces, and the body has its own frame, which orients it spatially from the global origin in the world, or in the geometry, in three-dimensional space. And then each face also has a frame that orients it relative to its own body, to its body's origin point. And so that looks like this. It has offset, rotation, and scale, so that you can do manipulations over a face or a body just by updating the frame. And then when you go to render it, you actually have to perform those calculations, but you're doing it only once. So, like, probably probably a big, probably one of the big things in this 3D modeling program, probably one of the major features, one of the major through lines will be taking multiple bodies and combining them, combining them together. And so you might have an object where you scale it, or you might have an object, for example, where you want to put the same object, like spokes on a wheel, for example, that you want to lay out in a circle and at different angles, but you want it to be the same part, like you want to have the same dimensions. Or you might have a part you have at multiple scales, big, little, and small, or somehow all combined. So giving the flexibility to do that here and express that here, rather than just baking that into the vertices of the faces, I think that's good. It avoids calculating these things into the last minute. So if you want to do a scaling, you can just, like, if you want to do a scale operation on a body, you can just update its frame and not have to calculate for all its faces what the effects are. And that also means when you're debugging, you can kind of ignore the frame and just render the face as it would, or render the body as it would be, or the face as it would be without the frame, and kind of get an idea of what it looks like in its purest form before you modify it. Because theoretically, the person who's working on this code, like the person who's using my CAD software to build a model, theoretically they're using the units and the dimensions that make the most sense to them. and then they're scaling it to meet the actual requirements. So I want it to be where they can express shapes and they can express models in intuitive units, whatever the intuitive means to the person using it, and then they can scale it to what they need, or rotate it to what they need, or offset it as they need. So that was something I considered when I built this, and the offset itself, like this part of it, and sort of the offset and the rotation together describe the exact location of a face. Well, I should say the frame and the offset and the rotation together describe the position of the face's origin relative to the body it sits on. So you start at the body's origin point, which is defined relative to the world, right? And then from there, you can then use the offset and the rotation to figure out the frame's origin point. I guess really just the offset. But and then the rotation and scaling come into play to decide how these two-dimensional vertices of the face loop map to three-dimensional vertices of the body or the model as a whole. So I think that's useful. I think that's good enough. Like, we're intentionally avoiding calculating things here. And like, we're avoiding calculating the exact position of things up front. We're giving ourselves the option not to. And in fact, when you do want to calculate the exact position of things, you're going to have to render this body to some other format, such as STL. Like, if you want to show a visual, like, with OpenSCAD, in fact, let me open that. Let me see if I can open a recent model. Open that one. Oh, okay. Well, let's try opening this one. Actually, let's just open recent. So you see here, we've got here a rendering of the model, and then we've got view. I want to show the editor as well. Hide editor. Nope. So you can see here we've got both the code and we got the rendering. So like, when you have the code, you're going to be defining a body of some kind, or a model which may contain multiple bodies. I'm not sure yet how that's going to work out. But your rendering that you see here in OpenSCAD, this fancy rendering that they've got, and I can't figure out there. I'm trying to figure out how to translate. Your rendering will implicitly require you to translate. You'll have to take this body and render it to another data type. And the reason is because this doesn't include enough information to put points there. You have to calculate it. You have to perform calculations to figure out where the face goes in three-dimensional space. Like, the face itself, this edge loop, if you look at it, it's a two-dimensional vertex. So it doesn't contain three-dimensional point data. It doesn't have the information of where exactly in three-dimensional space that vertex is, each of these vertexes are. So you have to calculate that information. So you have to render it somewhere to some other data type, and then at the point you've done that, it's then ready to display on screen. And I like that. I like having that separation between the theoretical, the abstract, and the practical. And the reason I like that is because A, you don't want to do calculations in advance that you don't need, and B, when you do the calculation to render like, see with OpenSCAD, when you're rendering here to the screen, you don't need high resolution. You need the lowest resolution that communicates effectively with the end user, the person using the software. So you need the lowest resolution that works. And OpenSCAD has, chosen a certain rendering quality that they use, a certain amount of detail that they give. But when you're rendering to an STL, you need a different, higher level of quality, because you need to be able to represent that shape accurately enough in the real world, like, for example, printing to a 3D printer. Excuse me. Let's go ahead and change back to my normal settings, hide the editor, and get out of here. Usually when I'm using OpenSCAD, I'll use Vim as my editor, which is why I normally hide it. Anyway, so with that said, like, I think this is a really good representation for the body, and it meets a lot of goals that I have for this project simultaneously. And I want to talk about those. I have those listed explicitly now, so you can read them with me. Basically, I see 3 stages to this project. First, we're going to have an MVP, which just does the thing. We're very close to it, actually. We're about halfway done with it, at least measuring by these bullet points. And then we need feature parity with OpenSCAD. That means replicating all the stuff OpenSCAD does, like all the different little functions it has for creating cubes and creating spheres and creating rectangles and translating stuff and doing matrices and all the stuff it does. We want to replicate the functionality, although not necessarily exactly the same way. We just want to be able to say, okay, if you have an OpenSCAD file that gives you a result, you can also use our language to get the same result, although you might use a different technique, or you might have to use a different approach. Because I want to guide the user toward approaches that are, I don't know. I know for a fact there are things I want to have different between OpenSCAD and here. And as part of that, getting we don't want to just replicate the functionality, like the modeling function capability that OpenSCAD has, which, by the way, Fusion 360 replicates that. That's not the only thing we need to replicate. We also need to have the command syntax to really truly get the OpenSCAD experience that we're looking for. And then once we have our own command syntax, a unique and beautiful command syntax, by the way, we're not just copying OpenSCAD syntax, because it's decent, but it could be better. So we're going to make sure we can describe the same models in this new command syntax as we could in OpenSCAD, and we want to make sure that when we render to an STL file, the STL file is equivalent to one that would be rendered from an OpenSCAD file from an equivalent OpenSCAD file to STL by OpenSCAD. So we just want to make sure we can do the same things and get the same result. Then I want to add later a translation layer, basically which translates OpenSCAD files into the command syntax of this program. And maybe command syntax is the wrong thing. What I really want is a programming language, I think. I think. Anyway, but I'm going to have some sort of domain-specific language for that. And then I have another quality check here. We want to make sure we can read in an unmodified OpenSCAD file, convert it to our internal command syntax or our native command syntax, then render it to an STL in such a way that it matches what OpenSCAD would do with the same file. So that's going to be really where we start getting excited about this project. And that's where it's going to really allow us to do basically whatever we can in OpenSCAD, barring any limitations where, like, oh, this program is memory inefficient, needs to be fixed, or that kind of thing, or any bugs or whatever. And then, of course, our ultimate destiny, which is inevitable and inescapable. Obviously, clearly, this is the way things are going to go. We're going to have superior performance to OpenSCAD. We're going to promote parallelism throughout the application. This is one of the big reasons for choosing Haskell. This is one of the big perks of this language. It helps you separate operations. It helps you create pure functions that definitely don't have any side effects that you have to worry about. And then you can have your side effects separately. Like, it allows you to use your type system to separate your side effects from your pure functions. And that's really a big win for us, because we can just go through and say, oh, okay, this certain calculation needs to happen in the IO monad, therefore it can't be parallelized. We can't use parallelism there. Maybe we can resort to concurrency, but we can't do parallelism. But, oh, can we take that calculation and extract the pure portion of it and then parallelize it and then make use of that result in the IO monad, so then we gain parallelism. So just being able to have an explicit separation between pure functions and functions where side effects are important is really, really helpful, and that's really one of the big wins of Haskell. And I'm hoping that's going to be much easier than in, for example, the C++ program, which is OpenSCAD. And concurrency, which is different than parallelism, it basically means the ability to coordinate multiple interdependent processes, which may or may not run at the same time. But the whole purpose of concurrency is to promote overlapping these processes as much as possible. So we have two processes that rely on each other. They both take results from each other, or one takes results from the other, or whatever. And our goal is to make them run at the same time as much as possible. So for example, the first process might run for a while and then wait for the second process to finish so it can get the result it needs. So you could just run process A until the stopping point where it needs to wait, then run process B, and then run process A once B finishes. You could do that. But what we'd rather do is start process A and process B at the same time, and then when process A gets to the point where it needs the value from B, it just waits for B to finish, but B might have already finished, so A might not have to wait at all. And it's going to be waiting less time overall because both of them can run in parallel as long as they're coordinated properly. So concurrency basically is a way to enable parallelism in more complicated scenarios where you don't have independent calculations. Memory. So one of the big challenges with OpenSCAD, I remember, I think I can actually find it. Hopefully it doesn't take too long. Oh, here it is, Beadloom. I was trying to create, is this even, here we go, yeah. You can see the performance on this part is really hideous. And you can see I have this shape that's repeated over and over again, and OpenSCAD is really not dealing with it very well. And basically, this is not something we get for free. This is not something Haskell just magically gives us, but this is one of my priorities for this project. I want to figure out a way to take these kinds of shapes and handle them well. And one of the things that kind of plays into that, I mentioned with a body, with the body and the face, they don't store all the information you need to render it, right? Some of the information you have to recalculate based on the body. But if I render a portion of the body, like say I render 3 faces, right? And then I discard that rendering information and just keep the end result, right? The finished, like basically the picture on the screen. And then I render to that same picture another 3 faces, and then discard the intermediate result and keep doing that over and over again. That would allow me to break up my calculations in a way to not have to worry so much about memory. And that is one of the concerns. I've noticed when OpenSCAD uses a lot of memory, it starts slowing down. Let's see if we can find it. Process name. Let's go by memory usage. OpenSCAD is here. It's not using that much, honestly. But I remember distinctly, like when I was working on this Beadloom project, I kept trying to make it bigger, and I couldn't because it ran out of memory. So I may have made this model smaller. But you can see even with the size it is at, it takes a lot of memory. And if we look at the... Oh boy, even opening the editor takes a while. If we look at this, we can see one of the main things we're doing here is we're creating arrays. Yeah, of bead tray cells. Let me see where the... Yeah, here we go. We have an array of beads, right? There's just basically a for each loop inside of a for each loop, and it's 10 by 20, and like making this bigger makes it impossible. Like it just slows down so much. So I was trying to make a big bead tray to make it quicker and faster to do weaving of beads, to do bead projects. That was something else I was working on a while back. And I halted that project because I just couldn't get OpenSCAD to even hold a file that big. Like it just kept locking up. And so like exporting to STL was just not practical. I did never try just getting rid of the preview and rendering directly to STL. That might have worked eventually if I just like rendered it and then walked away for a while. I don't remember what happened to that. But you can see it's taking forever to do anything right here. Yeah, okay. Here we go, let's just close it. Okay. Anyway, so there's that. And hopefully that all makes sense. Let's go back to what we're doing now, though. We're working on our MVP, our minimum viable product. And really what that really comes down to is being able to render the models to an STL file, and then having at least one piece of functionality to create an object, like to create a model. So like maybe a sphere, or like a function to create a sphere or to create a cube. That's really all I need to get past this point. It's just one piece of this functionality that we're trying to replicate. And so we figured out how to render faces to SVG. And the next thing is to learn how to triangulate faces, breaking down complex faces into simple triangles. Now, what we could do, and what we honestly probably should do, is go look at existing algorithms that are out there and try to understand them and replicate them in Haskell. Let me give you an example. Here's a library that does stuff. Probably I could give, this is probably a C program, and I could probably give, I could probably port this, or I could probably create a foreign interface to connect Haskell to the C library. I'm assuming it's a C library. But I'm not going to do that. I'm going to create my own triangulation function, and I just want to understand it. Like, I just want to learn more about it. So that's what I'm doing. We can get rid of all this stuff now, I think. There we go. That's what I'm doing, and yeah. Anyway, it's just because it's interesting to me. I've always wanted to. And I haven't always wanted to, but I want to now. Anyway, I like doing things myself and trying to gain understanding of it. I think that's the best way, long term, to understand a project. So once I've made my own, and it'll be horribly inefficient, but I understand it, then I'll be in a better position to choose another implementation. Oh, what change did I make here and not save? Oh, that. Okay, let's save that. Let's save everything. Okay, no changes. Good. Since you were here, I made sure to save the primitive module, which I forgot to do when I was committing. I ignored SVG files because there was one hanging out there. And I added project goals. Okay. So all of that said, let's do something. Okay, so our next step is to triangulate, and I don't remember. Well, first of all, let me look under render. Oh, okay, we don't have SVG rendering just yet. Model STL. I mean, we don't have STL rendering. Okay, there we go. Model STL. I knew I had some code. So here we have. Yeah, we have basically what this is. I took an STL file. I took a Wikipedia entry for an STL file, and I figured out, okay, you know, these are all the things you need for an STL file. You have a comment at the top. You have a list of faucets, and each faucet contains a normal and an edge loop, or a faucet loop in this case. And this loop contains exactly 3 vertices. I suspect it could contain more, but it apparently doesn't work in every tool to have more than 3. Like 3 is standard. Anyway, and for my purposes, a vertex is just a list of 3 doubles, right? And we remember vertex over here, right? This is a vertex. Remember here, it's. Oh, we need to run hascads. It's been a while. Now if I want to search for vertex, there it is. Okay, good. Okay. Great. Okay, so the next thing I need to do is do triangulation. And I have a bunch of calculations I've done here. Yeah, and you can see here, I was mentioning frames before. Here is the place where we would apply a frame to an edge loop. So the new normal and edge loop are relative to the coordinate space. I think this is probably not defined correctly. It probably needs to give a list of 3-dimensional vertices. But I hadn't gotten that far, you can see. I've got it to do here. But yeah, anyway, I hadn't gotten that far. And you can see where I was talking about things being inside the loop. This is something I was trying to calculate for a while before, and I realized, oh, wait a minute, I need to render this somewhere. Let me use Cairo and render it to an SVG. And so this is some of the calculations I've been doing. But I honestly don't know that I need this stuff. I mean, I know I need it at some point. I don't know that I don't know that I'm going to deal with this right now. I think, though, this is going to end up being an important file. We're going to keep that up on the side. And I'm probably going to start at the top of it anyway and just try to keep the same. Try to use the same file. Okay. So I don't need to go to 3-dimensional space in order to triangulate. So I think this is a valid function. It doesn't belong here. I'm going to leave it there until I have a better spot for it. Okay. So let's take the shape. Let's get rid of that interloper point because it's annoying me. So here's the interloper rays and the interloper point. We can just take everything after here and comment it out. And let's reload and run it. Perfect. Also, I want that to be brighter. I set it to 0.5 mainly because I was trying to understand. There we go. That's nice and bright. I was trying to understand how the colors work in Cairo when I did that, and I just never changed it back. But I'm going to undo those changes. I don't need to commit them. I just need to see it that way. Okay. In fact, I don't really need this file up at all. Now what I really want to do is take an edge loop like this and just go around the edge loop, starting at the first point, and then try to figure out where I can add triangles. Now, as a human looking at this, I would naturally want to start here and add a triangle there. That's just a really simple place for me to think about adding one to begin with. But in the software, I have to start here because that's the first vertex. And like, I can't rely on the first vertex being a good starting point. You know, this is a good starting point, this is a good starting point, however, this is a bad starting point. I don't actually want to make a triangle from here to there, although I could. You know what, maybe I won't worry about which triangles are good and which ones are bad, because what do I know anyway? Okay. Yeah, I mean, let's start out making triangles. Let's figure out a way where we consistently can come out with triangles. And then we'll worry about which are good triangles and which are bad triangles later, because we're not concerned about performance at the moment. And this triangulations function can be substituted out later on with no particular consequence. Okay, so that's what we're going to do. And so I do want a new type, though. I do. Model body. Data try face equals in equals try face tri-face offset. I don't think I need the normal thing, so I'm going to exclude it. And then tri-face loop. Yeah. You know what? Let's be honest. This is essentially a new type of face. That's essentially what this is. The only real difference is that we have specifically three vertices. Only three. Let's not do all that weirdness. Let's do face in. Excuse me. Okay. That's what I want. A tri-face is a face with exactly three vertices. And I'm not going to try to encode that in the type system for now. You just have to trust me when you see a tri-face that has three. And I think that's a fairly important distinction to make, I think. Although I don't know. It might turn out to be unimportant, especially since a new type is effective. I mean, what I could do is try to specify all three vertices of the face loop independently. Because what I've got right now is the triface. The reason it's a new type of face is because there aren't really any differences at the level of expression that I have, at the level that I've been expressing the type. But if I change this face loop to a list of three vertices, exactly three vertices in the type, like triface vertex 1, triface vertex 2, triface vertex 3, then the types would be different. And then there'd be a meaningful difference between the two. But that also would make it much harder for me to perform calculations because I would be constantly wrapping it in a list, unwrapping it, wrapping it in a list, unwrapping it. I think just leaving it in a list is much better, even though it's like as it is. I think, honestly, I'm not going to use the new type. I'm just going to use face directly. And maybe I use a new type, or sorry, maybe I use a type alias. But I think I'm just going to leave it as is for now. Like, I'm not going to complicate my life. I'm not going to try to distinguish between trifaces and faces at the moment because I think it's going to simplify things. This is hard. This is figuring out a lot of things. So what I really want to do is I want to have a function called triangulate that takes a face in and converts it to a face in, to a list of in faces. And what it does is break apart a complex face into a series of simple faces of simple triangular faces. Okay. That's what it does. Well, I'm not exactly sure how I'm going to deal with this function, and I'm going to deal with it. I'm probably going to change things. But here's one thing I know for sure. If the face loop consists of if the face loop consists of exactly three vertices, then we return the face by itself. Okay, we know that's for sure, because if it's already a triangle, we leave it alone. Okay, now let's say we're going to triangulate this shape here, and remember this is the starting point. It needs to work for any starting point, but that's something we'll test later. What I want to do is from this point make a triangle. Or skip it. I can skip sometimes. Well, let's think about what we really need. Let's try to break it down. Okay. In order to break apart one face into multiple faces, we need to make sure every vertex is represented in at least one face of the resulting simpler faces. The triangles have to contain every vertex. So we have a series of triangles that have to contain every vertex. And we have 1, 2, 3, 4, 5, 6, 7 vertices total. And we're going to need to divide this into triangles in some way. So I wish I had some good marking software here. I guess I can use GIMP for this, but this is going to be a bit overkill. Open. Core test 2. Open. Let's give it a resolution of 72 pixels per inch because that's more faithful to the original. And We want a width of, say, 200. 500. Okay. Here it is. Great. Now let's add a new layer immediately. No, what? What just happened? I don't want a new image, I want a new layer. I haven't used them in a while. At least Control-Z works. Okay. Let's pick another color. Cyan, that's a good one. Now, we're starting from this point. Well, okay, here's what I want. Oops, that's not what I wanted. Let's take, we want the line tool. I think this works actually as a line tool. So here's, Okay, that worked. Here is an idealized shape, right? One, two, three, four, five. Okay, that requires 5 triangles, and we have 7. We have 7 vertices. So that means almost all the vertices are shared. Every vertex except for these 2 are shared between multiple triangles. Okay. So let's try it a different way. Let's try overlay 2. Name doesn't matter. Okay, so let's start from this point. And let's build a triangle from here. How do we do that, though? We don't really have... There's nothing here to triangulate against. Is there? Okay. There is a place we can triangulate. We can go from there to there, or from there to there. Okay, that makes a triangle. Okay, we've done that. We go to here. Well, this is already part of a triangle. We don't need to do anything. This one's already part of a triangle. We don't need to do anything. Go to this one. Okay. We could triangulate here. Nope, that's not a triangle. So we're making a new vertex here. So if we go that, so there are wrong ways to do it, and we have to figure out what those are in advance. Okay. Because you see here, we're making a new vertex in order to do the triangles. Because if you put this line across here, this triangle works, but this other triangle doesn't. Because we already have the angle set here. We can't change the angle and go here. We can't bend it like that. Right? That doesn't work. It's not a triangle. It needs to go straight across. And effectively following this grid line here, it needs to go straight across to there and create a new... what do you call it? That size is too small. Let's make it like 10 or something. Better. Yeah, that's better. So that doesn't work. You can't go from there to there because it breaks the rest of it. Okay, so let's say we tried that. It didn't work, so we go back to the beginning. And we skip this one. Then we start here. We go there, there, and suddenly this works. Okay. We skip this one, it's done. We go to this one. Can we make a triangle from there? Well, specifically, can we make a triangle to the next one? Yes, we can, right here. Boom. Okay, and we have this open area here. We skip that one, we go here. Can we make a triangle from there? We can. Okay. So then we can skip this one, go here. Can we make a triangle from there? We can make 2 of them. Boom, done. And all of this works out. The entire shape is now in triangles. One of the issues I'm seeing here is I need to figure out a way to keep track of all the triangles I made previously. And I need to be able to keep track of which vertices are part of which triangle as well. So I need to make sure that... Yeah, okay, let's add another overlay here. Because I think we've got a good process. So I'm not doing the same thing again. Change colors here. Okay, we need to make sure that every vertex is in at least one triangle. Fine, that's easy enough. But we also have to make sure that all the space inside here is in a triangle, right? For example, let's get rid of that line. And we just made this line from here to here. How do we know we're not done yet? How do we know that, okay, this is a triangle. How do we know this isn't a triangle? You know, we've created this triangle, that triangle, that triangle. However, no, I think what we need to do is just go around to every vertex. Control-Shift-C, I think. There we go. Yeah. Here's what I'm thinking. When we go around to every vertex, if we follow the rules at every single vertex, then, and we don't skip it unless we should skip it, then we will guarantee the entire shape is part of at least one, it's part of one of the triangles. And we guarantee that every shape that's remaining is a triangle. Because if the entire interior is part of a triangle, that means that all the interior must be triangles. Because, you know, yeah. Because this wasn't a triangle until I added this line here. Then it was two triangles. So at this point, we've guaranteed, once we've gone through all the points, we've guaranteed we have all the triangles we need. I think this process works. And obviously, this is a different process than what I got when I went through it by hand. But now maybe it's not that different. Let me create a new layer. Let's create overlay 4. Oh man, these are really confusing. Let me get rid of 3, just keep it going. And I'm going to temporarily get rid of this one. Now let me go back to the process I was doing by hand. We start from here, we go here. Oops, gotta learn how that works. We start from here, we go there, and then we go down to here, and we go there. Then we go to here, and we go there. Then we go to here, and we go there. So this is what I was doing in my head mentally. This is how I was dividing it, slicing it. So it's basically going through here like that. I'm cutting up that way, but you can see the results are, okay, they're not the same, but they're similar. And I don't really have any reason to believe that this is inferior to this. I don't have any particular, like, does one of them perform better than the other? I mean, is the number of triangles different? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They're the same. I don't see any particular way that they're different in terms of just calculations, right? Like, now, as far as rendering this to an image, well, there might be some weird differences I don't know about, but actually there probably aren't, because this is a flat surface. We're not talking about a body here. We're talking about a face. We're trying to triangulate a face. The face is already on one plane. It's flat. It's only in 2 dimensions, or it only expresses itself in 2 dimensions. So we should be good here. Yeah. Yeah, so I think this is fine. So what is our method? Our method is we start from this beginning point, and we just dumbly try to connect 1, 2 across to there. Then we skip 1 and start from there and do it again. Skip here, connect to the next one, if it's possible. And if it isn't possible, we start from a different starting point. And it may not always be possible to follow that dumb algorithm. It may not work for every shape, but this is a good starting point. And if it doesn't work, we'll figure out why at that point. Oh, and one of the main things I wanted to do, actually, let's try to reapply the same technique. Okay, I'm getting really confused. Let's start here. Okay. What's that? This is me doing it by hand, isn't it? It is. It's the same as that. I'm going to keep overlay 4 because it's better. Delete. Doing it by hand. Try by hand. Try from second point. This one no longer serves a purpose. That was illustrative. Okay. So I'm going to try it again. Don't remember the name. I don't know what name. I don't remember what I'm doing. So we take this one. We try to go 1, 2. We try to go to here specifically. Bam. Okay. Then we skip this one. We go to this one. We try to go 1, 2. Boom. But this is outside, so that doesn't work. So at that point, we calculate. We do a different method. So we skip that one, then, and we go to here. Start with this one, skip 1, go there, boom, works. Skip it, go here. And then this one does a triangle here. Skip 1, go here. Okay, skip to there, and then start from this point. Skip 1, go there. It works for the shape anyway. And then from here, we can't skip 1, go there. We can't do that. We have to go to here. So we have to keep skipping till we get something that works. So far everything's worked out. We try going here. Oh, you have to skip that no matter what. Okay, we can't go here because it crosses another triangle and adds a vertex. It's just a weird vertex. So we can't go there because it crosses another triangle, but we go to the next point, available point. Okay, so I think our algorithm is connect the point you're on to the next available point that doesn't cross an existing triangle. Boom. Then, starting from that point vertex you just connected to, do it again. And that's the first one available. I think that works. I mean, it works so far. I mean, this is just one shape, and I can think of more complicated ones where it'd be confusing. But this is where I'm going to start. Whew. Yeah, I'm not going to torture test this yet. I'm going to actually code it. Because I think it's important to... Yeah. I think it's important to make this progress explicit. Like, we just did a lot of thinking. We need to write it down in some code and get it to something tangible. And then we can torment and break it. Okay, so... Try strategy. Triangulate 1. Attempt to triangulate from the starting point, like so. Add a line from the current vertex to the next upcoming vertex where we do not not go outside the shape, and we do not cross an existing triangle, a prior triangle. Okay. There. If the If the result doesn't work, try a different starting point. Let's try this again. Okay, we want to try to see what happens. Okay, so what I want to do, remember, this is the first vertex in the edge loop. I want to try to follow these rules. Okay, that's not a triangle. That's a triangle. It works. Now, from this point, we can't go there. We try to go here. Oh, that doesn't follow the rule. That doesn't either. That goes outside the shape. That doesn't either. That goes outside the shape. Ah, there we go. At this point, we can already discover it's broken at that point. Okay. If there's no solution, skip to the next vertex. I want to see, can I salvage this? Can I take this thing and salvage it somehow so that we don't have to restart it, the whole process? Okay, so we're starting from here. It didn't work. It failed. It bombed out. So we go to here. No, we can't salvage it. And the reason is because... The reason we can't salvage is because we have to add a new vertex. There's no way not to add a new vertex at this point. Why? I think the reason is because this angle is concave. But, look at this one. This angle is also concave and it doesn't cause an issue. Oh, whoops. This angle is also concave and doesn't cause an issue. I better go see what I broke. Okay, good. Look at that. Yeah, concave. And this is concave, and there's no issue. So it's not because that angle is concave. It's because this line is pointing in, right? This line here is pointing in to the shape. Yeah, okay. So with this angle up here, this line points out. This line points out. But with this vertex over here in this corner, one of its angles points inside. Meaning, we shouldn't use that as... That vertex should only exist in one triangle. We shouldn't draw a line to that point because... Okay, so I need to write that down. Add a line from the current vertex to the next upcoming vertex where the current vertex A to the next upcoming vertex B, where we do not go outside the shape. We do not draw outside the shape. We do not cross a prior triangle. This really should go here. And the vertex B does not, and neither edge from vertex B points are endoscopic. Pointing into the shape. There's probably a word for it. Congruent Okay. Endoscopic. I really want the etymology here. Endoscope. An illuminated, usually fiber optic, flexible, or rigid tubular instrument for visualizing the interior of a hollow organ or part, such as the bladder or the esophagus, for diagnostic or therapeutic purposes. So it sounds like a camera in the body. Typically has one or more channels to enable passage of instruments, such as forceps or scissors. Okay, Greek endo means inside. I knew that. Okay. Modern endoscopy required the invention of the electric bulb and then fiber optic cable. So the first modern endoscopes date to only 1967. So in the 1860s they had a crude one. The endoscope may be inserted through a natural passageway or through a tiny cut in the skin. I mean, it makes sense because the endoscope is pointing into the body. I think that's a really pretty good coinage there. Face. Into the face. Let's be more specific than body. Okay, let's try these new rules. Do another try. Okay, so here's the first vertex in the shape. Boom. We can't go there. We can't go there because it violates our endoscopy rule. Can we go here? Well, that's not a triangle. We add at least one triangle to the shape. It's not a triangle. Well, if we're adding at least one triangle to the shape, that means there are only two candidates. There's this one and this one. Those are the only ways I can add a triangle from here. Yeah. Those are the only two choices. Okay, so let's reword this algorithm. From the current vertex A, identify the two vertices B1 and B2 to which we could draw a line from A which adds a new triangle to the face. Okay. Between those two vertices, B1 and B2, choose the first one, which follows all of these rules. Choose the first one which follows all these rules. The new line does not draw outside the face. The new line does not cross an existing triangle. Okay. Neither edge of the B star vertex is endoscopic, meaning it doesn't point into the shape, into the face. Okay. If either edge, if between two vertices, choose the first one which follows all these rules and name it B. If B if neither B1 nor B2 follows those rules, skip vertex A and try again from the next vertex. If this is like a 1, 2, 3 process, really. 1, 2, 3. Again with the next. Okay, so if neither B1 nor B2 follows these rules, skip vertex A and try again with the next vertex on the face, on the edge loop. Okay. Get rid of that. Get rid of that. Great. Step 4. Continue oh yeah. If you find an adequate B point, make that be the next. Consider that 10 minutes. Consider that point. Thanks, babe. If you find an adequate B point, consider that point your new A and do the process again. When do you stop? I don't know. I don't know. So this is the tricky thing. When do you stop? I don't know. I don't know. And yeah, I need to quit for now. I need to quit for the day. But this is good progress, actually, getting this process down. So the goals that we've managed to accomplish here are, we have a process that's mostly same, but the most important thing is, if we start from here and we try going this way and it doesn't, like if we start from here and try going this way and it doesn't work, we're able to correct immediately rather than waiting till we get to the end and realizing the shape doesn't work. But now what I got to figure out is, how do I stop? So let's follow this new process and find the stopping point. I want to put these side by side. Can I do that? What's that do? Nope, don't want to do that. I'd like to hide those tabs, but I don't want to like make them hidden forever. Just want to hide them for now. Okay. Well. There we go. Okay, that's something. View, show. Fill windows, show tabs. Okay, I don't care about that. Oh, let's turn single window. Yeah, there we go. Boom. Perfect. We get rid of these guys. Get them out of our way. Perfect. Okay, great. Let's go here and make this. I don't really want it always on top, actually. What I want to do is just get rid of these, get them out of my way. Perfect. Okay, so actually, I need a new layer first. New layer. Trying again and again. Hide the old layers. Good. Now we can start from here. Okay. Now, we try going here. It doesn't work. Then we try going there. It does work. We get our triangle here. It follows which rules? The new line does not draw outside the face. Check. There are no existing triangles to cross, and neither edge of the B vertex is endoscopic. Check. We followed all the rules. Okay. Now, we start here, we consider this our A point, and we try again. You could make a point in this direction. That's the only choice, because we already made this triangle, so this is the only other remaining choice. Okay, the new line, not double back over previous line. Obvious, that's obvious, but I want to write that down in case I forget. Okay, boom, it's obvious at the moment when we're looking at all this stuff. Now then, from this point, I can go back here, which I can't do now, or I go here. No way, this is like working. 1, 2, 3, 4. Wow! This is an alternative solution, right? No, it's not, and I'll tell you why. This part right here is not a triangle. And what we need to do is add a triangle right here. We need to add a triangle there. Like, this may happen to be a triangle just by chance. These 3 points may be lined up just by chance. But that's not guaranteed for every single shape. Like, it looks lined up and it's convincing. Like, this may be a triangle, but maybe it's not. So like, and also the more concerning thing is this line doesn't follow any of these rules, because we're drawing a line between random points. Wait, maybe it does. Hang on a second. I've got an idea. It's a good one. New layer. Subshape. This might be enough. We start from this point, we go here. Now what I'm doing is I'm going to encase the area which is, quote, not part of a triangle. And I'm going to exaggerate the part that's messed up just so you can see it. Like this part, obviously, it's not a triangle. It's a 4-pointed shape. I wish I'd exaggerate that a little bit more. I think I will. So this is going to be we're entering a fantasy land here a little bit, because this is not actually how the shape looks. But I think it's more useful. So we'll just pretend that's a subshape of the original shape. So this blue line here. So our next step is going to be, once you can't continue, check, find any remaining subshape, subface, which is not triangular. If there are none, stop. If there is one, perform the same process for that subshape, subface, and concat the triangles together for all subfaces together. Bam. Okay. So now we're going to take and hide the original and that. So then we're going to start from this subshape. And we're going to perform the same calculation again. See, because when you look at the original face, these 2 points here are very far apart from each other. They're not the next available triangle. You know, skip one thing. But when I limit myself to just the subface, it is. You skip one here. So the following rules, the rules will work. Yeah, the rules will work. So then we got these two are triangles, in addition to all the other triangles, which I'm not seeing all of them anyway. In addition to all the other triangles. So let's see. Yeah. 1, 2, 3, 4, 5. So then we have all 5 triangles there. Okay. And it looks like 5 triangles is the minimum. Like I've made several different solutions and couldn't get lower than 5. So maybe that really is the correct solution, like, or the ultimate solution. I don't know. Anyway, I think that's a really good stopping point. We have described exactly what we're supposed to do. I better save this sucker. Save core triangulation test path dot png. No, dot gimp. Dot xcf. Boom. There we go. So, like, that's going to be useful for me when I come back to this, these two things. So I think when I go to write this function, it's going to be very clear and evident how to write it. I think it's going to go very quickly. Certainly a lot quicker than it took to make up these rules. So this has been a good exercise, and we've made a lot of progress even though the code hasn't really changed. Okay, so that's where we're calling it. This is probably my last stream for today, because, you know, life. All right, have a good one.